Hello everyone, welcome to this session. Before starting today's session, let us see what we discussed in the last class. If you recall, we started with the orifice and mouthpieces. We defined this orifice. Orifice is an opening provided in the side of the tank or at the bottom of the tank. Most of the time you are going to see this opening at the side of the tank. Okay, that is the definition of orifice. Now both orifice and mouthpiece, they are used to measure the discharge. Now we didn't define what is a mouthpiece. I am going to define that mouthpiece today's class. So before actually going to the mouthpiece, so let us see what is this definition of mouthpiece, in what way this is different from orifice. Now basically this mouthpiece is a short tube. I repeat, mouthpiece is a short tube whose length is equal to 2 to 3 times the dia of the orifice. I repeat, mouthpiece is a short tube whose length is equal to 2 to 3 times the dia of the orifice. In other words, so most of the times this short tube, or in other words the mouthpiece, is connected to the orifice. The next question, when I have the orifice, what is the necessity of going for a mouthpiece? Now it is observed that the coefficient of discharge in case of a mouthpiece is higher than that of the orifice. I repeat, the coefficient of discharge in case of a mouthpiece is higher than that of the orifice. Recall in the last class we defined this hydraulic coefficients. So this 4 hydraulic coefficients we defined: coefficient of discharge, coefficient of velocity, coefficient of contraction. In addition to that, we also defined what is known as coefficient of resistance. If you recall, this coefficient of discharge, which we used several times while solving the problems, and also right from deriving an equation for this venturimeter, we started using this term called coefficient of discharge. What is this coefficient of discharge? It is the ratio of actual discharge to the theoretical discharge. Now we studied this ideal fluid and real fluid. When I am talking about a ideal fluid, we are not talking about any losses. So if that is the case, the discharge you are going to find for a ideal fluid is much higher compared to that of a real fluid. That is the reason, if you want actual discharge, you need to multiply this theoretical discharge by this coefficient of discharge, CD. Now I also said this CD is always less than or equal to 1. Then we started deriving an equation for this discharge through the orifice. Now we also discussed about the types of orifices. So we started with a small orifice, big orifice. Depending on the shape, we have a circular orifice, we have a rectangular orifice, we have a triangular orifice. Then depending on the edge conditions, okay, so we have what is known as sharp edge orifice and bell mouth orifice. Then depending on the discharge conditions, we defined three cases. One is orifice discharging free, then fully submerged and partially submerged orifices. These are the things we discussed in the last class. Then so I promise you that we are going to derive an equation for this sharp edge orifice. Let us start with that in this class. Discharge through the orifice. Now these derivations are very simple. Basically you need to remember two formulae. What are those? One is a law of conservation of mass, the other one is law of conservation of energy. If you know these two equations, the derivation of these equations are very simple. Now in order to derive an equation for this discharge through the orifice, kindly refer to the figure what I gave here. Now this is the most of the things what I mentioned here you studied in the second chapter, pressure and its measurement. Okay, so we all know that at the free surface of the fluid we have atmospheric pressure. Why atmospheric pressure? Because this is surrounded by atmosphere. This atmosphere exerts a pressure on the surface. That pressure we call it as what is known as atmospheric pressure. That's what I presented here. The red arrows what I presented here is the atmospheric pressure. Now there is a tank, and on the side of this I provided a orifice. Now In the last class, we also defined what is known as venacontracta. What is this venacontracta? I didn't mention the salient features of this venacontracta. At venacontracta, the jet has a minimum cross sectional area. Okay, I repeat, at venacontracta, the jet has a minimum cross sectional area. The first condition. The second condition is the streamlines are parallel to each other. Okay, the streamlines are parallel to each other. The third condition is pressure at venacontracta is atmospheric pressure. You should not forget these three conditions. Again, I repeat, at venacontracta, the pressure is atmospheric, the streamlines are parallel to each other, and the jet has a minimum cross sectional area. Now, once the jet passes through this, out of this venacontracta, the jet diverges again. Okay, so in the last class, I somehow missed these 3 points. So kindly remember, whenever you are talking about a venacontracta, these 3 salient features are very, very important. So minimum cross sectional area, pressure is at pressure atmospheric, and the streamlines are parallel to each other. Now, so what is this venacontracta? In the last class, I said the momentum of the flowing fluid cannot be changed abruptly. For example, if you talk about a fluid particle, okay, lying very close to this solid boundary of this container, so once you open this orifice, so these fluid particles, they start moving towards the orifice. How they are going to move? They start moving along the boundary of this container. Okay, so remember, when it comes to this point, okay, the direction of the flow is like this, or the particle is like this, and if you talk about a particle from this side, it is moving straight downwards, but the moment once it touches the upstream, upper edge or the lower edge, suddenly there is a change in the flow direction. Now, whenever there is a change in the flow direction, since the momentum of the flowing water cannot be changed abruptly, it tries to continue in the same direction for some time, then it starts moving towards the outer edge or through the orifice. When in doing so, these fluid particles, they lost some energy. So that we call it as what is known as, so the jet or the dia of the jet get compressed there. Okay. Now at venacontracta, that is the reason I said the jet has a minimum cross sectional area. The point where you are going to see all these 3 salient features, the jet has a minimum cross sectional area, streamlines are parallel, and the pressure is atmospheric, that point we call it as venacontracta. Again I repeat, after the venacontracta, the jet diverges again. That point is very, very important when we are talking about orifice and mouthpiece. With these basics, let us consider a orifice, so fitted to a side of a tank, okay, as shown in the figure. Consider a streamline. I consider a streamline inside the tank. Okay, I consider 2 points. Okay, point A here, and this I called it as B. Unfortunately, it is missed here. Kindly note down at this point at venacontracta, the point on the streamline I considered is B. Okay, so that's what I mentioned here. Consider 2 points A and B. Point A is inside the tank, and point B is at venacontracta. So point A inside the tank, and point B is at venacontracta. Point A is at a depth of, this is capital H from the center of the orifice, and B is on the center of the orifice. Look at this, the blue line what you are seeing is the center of the orifice. Now from the center of the orifice, this point A is at a depth of small h, okay. So I represent this as small h, fine. So this is small h, and my point B is exactly over the center line. Therefore, here my Z1 is equal to h, and here my Z2 is equal to 0. Again I repeat, so point A is at a depth of h from the center of the orifice, and point 2 is exactly on the center of the orifice. Now again, my Z1 is equal to h and Z2 is equal to 0. Let us define this P1, the intensity of pressure at A, V1, velocity of flow at A. This V1 is also called what is known as velocity of approach. What is this velocity of approach? Velocity of approach is the velocity of the fluid particle at which it approaches the orifice. I repeat, velocity of approach is the velocity of the fluid particle at which it approaches the orifice or the outlet. For example, if the tank is very small, then there is some velocity at V1. Suppose if you talk about a big tank or a reservoir, remember from the dam face to the remote point, it is running in terms of kilometers. Okay, if you talk about a big dam, the length from the dam to the remote point is maybe about 2 kilometers or 3 kilometers depending on the topography. If that is the case, suppose if I consider a fluid particle from the farthest point and the velocity at which it approaches the gates at the dam is almost negligible. That is why in the studies most of the time we neglect this VA as negligible or VA is equal to 0. Again I repeat, V1 is also called VA. VA is called the velocity of approach. Velocity of approach is called is defined as the velocity at which the fluid particle approaches the outlet or the orifice. If the tank is very big, velocity of approach is negligible. Then we define this P2 and V2. What is this P2? The intensity of pressure at Cc. V2 the velocity at Cc. Okay. Now we know that this is what I mentioned at the beginning of this class. At venacontracta, the pressure is atmospheric, streamlines are parallel to each other and the jet has a minimum cross sectional area. Now here at this point, just now we defined the pressure at this point is P2. Now I am going to replace this P2 by P atmospheric. Okay. So that is very important. Now once you define these terms, apply Bernoulli's equation between point A and point B. Okay, what is general Bernoulli's equation? The total energy at point A is equal to total energy at point 2. That is, total energy all along the streamline remains the same. So total energy consists of 3 energies: pressure energy, kinetic energy and potential energy, or it is also called datum energy. So let us write the general Bernoulli's equation: P1 by gamma plus V1 square by 2G plus Z1, that is at point A. At point B, P2 by gamma plus V2 square by 2G plus Z2. Okay. Now what is P1 by gamma? P1 by gamma is, just go back to the figure again. Look at this figure. Now I want the pressure head at this point. Pressure head at this point is given by the vertical height from point A to the free surface. What is that? Now from the center of the orifice to the free surface, this height of water or depth of water, we represent this as capital H. Now from point A to the center of the orifice we defined as H. Now I am looking for this vertical height. So this vertical height is capital H minus small h. Now remember, at the free surface you have atmospheric pressure. That is, my P1 by gamma is equal to P atmospheric plus this H minus small h, capital H minus small h. Now at Cc the pressure is atmospheric pressure, therefore my P2 I am going to replace by P atmospheric. So then Z1 is small h and Z2 is equal to 0. Substitute these values in that Bernoulli's equation, see what you are going to get. Look at this, P2 by gamma is for P atmospheric. Why? Because P2 is at venacontracta. P1 by gamma is equal to P atmospheric plus capital H minus small h. Z1 is equal to h, Z2 is equal to 0. Substituting these values in the above equation, that is this equation, we have P atmospheric plus h minus small h plus V1 square by 2G plus h, that must be equal to P atmospheric plus V2 square by 2G plus my Z2 is on the center of the orifice, therefore Z2 is equal to 0. If you simplify this, look at this, minus small h plus small h gets cancel each other. So you left with this capital H plus V1 square by 2G, that must be equal to this V2 square by 2G. Now remember, there is P atmospheric term. So this and this gets cancelled. So you will left with this H is equal to, so push this V1 square by 2G term to the right hand side, you are going to get V2 square by 2G minus V1 square by 2G. Now just now I said this V1 is called the velocity of approach. If the tank is very big, then velocity of approach may be negligible and most of the time we consider this as 0. If that is the case, my equation reduces to H is equal to V square by 2G. Okay? So I am looking for this V2. V2 is equal to root of 2gh. What is this equation called? This equation is called Torricelli's equation, which we derived in case of a pitot tube. So V theoretical is equal to root of 2gh. That is called Torricelli's equation. Now V2 is given by root of 2gh. Then what is the discharge equation? Continuity equation. Q is equal to A1 V1 is equal to A2 V2. Since I know this value of V2, so what I am going to do is, in order to find the value of Q, I consider this A2 V2. So what is A2? A2 is the cross-sectional area of the jet at venacontracta. Okay, and V2 just now determined. If you substitute the value of A2 and V2, you can easily calculate what is the amount of discharge that is flowing out of the orifice. So this is the discharge equation for an orifice having a sharp edge. Remember, in the last class we defined the sharp edge orifice and a bell mouth orifice. So I said, in case of a sharp edge orifice, the jet has a minimum contact point with the water or fluid, whereas when I am talking about a bell mouth entrance, so all along from the upstream edge to the downstream edge, the fluid is in contact with the edge. That is how we differentiate between sharp edge and bell mouth orifice. That is about equation for discharge through a orifice. If you go to the laboratory, so you need to conduct an experiment to determine this hydraulic coefficient. Okay, what are the hydraulic coefficients? CD, CC and CV. If you recall, in the last class I said, most of the time finding the exact location of this venacontracta, I repeat, finding the exact location of the venacontracta along the jet is very difficult. First problem. Second problem is, once you identify the point where venacontracta is formed, then measuring the dia of the jet at venacontracta is another difficulty. I repeat. So first thing is identifying the exact location where venacontracta is formed is the first difficulty. The second difficulty is, suppose if you identify the place where exactly this venacontracta is formed, then finding the dia of venacontracta is very difficult. Okay. So usually what we are going to do is, in order to find this coefficient of contraction, we make use of the relation. What is that relation? Now the relation we know is coefficient of discharge is equal to coefficient of velocity into coefficient of contraction. You can easily determine the coefficient of discharge. You can easily determine the coefficient of velocity. How you are going to find the coefficient of contraction? Coefficient of contraction is equal to coefficient of discharge divided by coefficient of velocity. That is what we are going to discuss in this topic. Now, the same setup what I showed here will be there in your laboratory. Okay, there is maybe a tank or a channel. So there is a orifice provided here, and on the downstream side there is what is known as a measuring tank. Let us first talk about coefficient of discharge. Here I mentioned about coefficient of velocity. Let us first discuss about coefficient of discharge, then we will come to coefficient of velocity. Now what is this coefficient of discharge? Coefficient of discharge is equal to actual discharge divided by theoretical discharge. Okay. So actual discharge is equal to coefficient of discharge into this theoretical discharge. Now how to find the actual discharge? Now for that, look at this. So there is a constant supply here, okay, and the dotted line represents the center of the orifice. Now using this constant supply, you maintain a constant head. I repeat, using this constant supply of water, you maintain a constant depth. For example, if I maintain a constant head of H1 is equal to 10 centimeter. Okay. Now then allow the water to flow through the orifice. Okay. Now on the downstream side there is a measuring tank. Okay. Now you know the length and breadth of the measuring tank. The only variable is the depth. Suppose I take a stop clock at time t is equal to 0. So I note down what is my initial level. I repeat, I take the stop clock at time t is equal to 0. Okay, the depth of water in the measuring tank is, I call it as small h1. Immediately start the stop clock. Collect the water for about say 30 seconds or 60 seconds or maybe 90 seconds depending on this measuring tank. Say for example, if I collect this water for about 60 seconds, at the end of 60 seconds, okay, note down the final water level. Most of the time there is a small glass tube attached to this measuring tank, and next to the glass tube there is a measuring scale. At time t is equal to 0, make a mark on the scale. At time t is equal to 60 seconds, make a mark. Then I call this depth as h2 and the initial depth as h1. Small h2 minus small h1 will gives me the depth of water collected for 60 seconds. I hope it is clear. The next question is, sir, why did you consider only 60 seconds? Why not 30 seconds? Why not 45 seconds? Why not 90 seconds? Hey, you are welcome. Absolutely, there is no odd and fast rule that you need to collect only for 60 seconds. It is your wish. Okay. Then, what is the volume of water collected in the tank? Volume of water collected in the tank is given by area into depth of water collected. Okay. So, L into B is constant. Okay. The only variable I said is the depth, that is h2 minus h1. That gives the volume of water present in the measuring tank. Suppose if I divide this volume by time, I am going to get what is known as discharge. L into B into h2 minus h1, that is meter into meter into meter cube divided by time 60 seconds, you are going to get this meter cube per second. Okay, that is a discharge. Now remember, you are measuring the actual discharge. That is, whatever the discharge or flow coming out of the orifice, that is collected in this. Okay. Now, once you know this discharge or calculated this discharge, now Q actual is equal to CD into Q theoretical. What is Q theoretical in this case? A into V. So, what is A? A is the cross sectional area of the orifice or at venacontracta. What is V? V is the theoretical velocity. What is theoretical velocity? Root of 2gh. I said for every trial you are going to note down this value of h. Okay. So, area is constant, the only variable here is h and the variable here is the head of water. Knowing these two values, you can easily calculate the coefficient of discharge. The same thing you are going to do in your laboratory also. This is about finding the coefficient of discharge in the laboratory. Next one is how to find this coefficient of velocity. Okay, in order to find the coefficient of velocity, so what we will do is consider a jet of water. On this jet, okay, consider a point P. Now, this point P has a coordinate x and y. That is, this point P is at a distance of x from the venacontracta and y from the point P to the center of the orifice. Again, I repeat, this point P has a coordinate of x comma y. This point P is at a distance of x from venacontracta and at a depth of y from the center of the orifice. That is what I mentioned here. Look at this. Let H, the constant head of water in the tank, supplied by a constant supply as shown in the figure. Let Cc represents the venacontracta. Consider a point P of x comma y on the jet. Point P is at a distance of x from Cc and y from the center of the orifice. The same thing I mentioned earlier. Now, let T, I define this T as the time taken by the fluid particle to move from this Cc to this point P. I repeat, let T, the time taken by the fluid particle to move from Cc to this point P. Then, what is the horizontal distance covered by this fluid particle? Horizontal distance travelled by the fluid particle is given by, so this x is equal to V actual into T. remember velocity is distance travelled divided by time. So, therefore, distance travelled is equal to velocity, actual velocity into time. Okay, simple relation. I call this as equation number 1, where V actual is the actual velocity. What is the vertical distance? So, vertical distance is, kindly go back to your high school where you studied these equations. S is equal to ut plus half at square. Okay. Now, in this case, what is the vertical distance? Vertical distance we represented as y. Therefore, I am going to replace this s by small y. So, what is the initial velocity? When I am talking about initial velocity is 0. Now, what is Ga? So, it is acceleration due to gravity. Therefore, I am going to replace this a by g. If you do that, the equation s is equal to ut plus half at square reduces to y is equal to 0 plus half gt square. If you simplify that, you are going to get 2y is equal to gt square, or t is equal to root of 2y under g. But consider the equation 1. What is this equation 1? X is equal to V actual into t, or V actual is equal to x divided by t. Now, from equation 1, V actual is equal to x divided by t, and what is the relation we are looking for? We are looking for coefficient of velocity. We define this coefficient of velocity as actual velocity to the theoretical velocity. Now, theoretical velocity is given by Torricelli's equation root of 2gh. Therefore, my Cv is equal to, if you substitute these values, it will be it is reducing to x divided by t whole thing divided by root of 2gh. If you simplify this, you are going to get Cv is equal to x square divided by 4yh. Again I repeat. So, this Cv is equal to x square divided by 4yh. Now, in this equation, so I did a mistake. What is the mistake? The mistake I did here in this case is, so here I represent this, the depth of water in the tank as capital H, whereas in the derivation I forget to put it as capital H and I put it as small h. Kindly make this correction. This is root of capital H. Okay. Then in that case, my Cv is equal to x square divided by 4y capital H. Okay. Now, look at the beauty of this equation. If you know the value of x, if you know the value of y, and if you know the value of capital H in the tank, you can easily determine what is the coefficient of velocity. Okay. Now, usually in the laboratory setup, there is a x scale attached to this tank, and to this x scale at regular intervals you have what is known as vertical, y scales. So, there are two ways of conducting this experiment. One is, so you can fix the value of x before conducting the experiment. Maybe if I choose my value of x is equal to 20 centimeter, what it says? It says that I need to operate my y scale at only 20 centimeter. I am not going to touch the y scales at other points. Or, sir, I am going to change my x and y from trial to trial. Yes, you are welcome. In the first trial, you may take x value of x is equal to 10 centimeter. You are going to vary the y scale there. For example, in the second trial, you may fix the value of x is 20, and you are varying the y scale only at 20. For the third trial, maybe x is equal to 25 centimeter. You are varying the y scale at 25 centimeter. There is no hard and fast rule that you need to fix y, you need to fix x and all. It is your wish. So, what I mentioned here is, if you know the value of x and if you know the value of y and if you know the value of h, you can easily determine the coefficient of velocity. You already determined the coefficient of discharge, you have the coefficient of velocity. Now, then coefficient of contraction is equal to coefficient of discharge divided by coefficient of velocity. This is how you are going to find the hydraulic coefficients for this orifice in your laboratory. I hope it is clear. This is what I mentioned earlier, determination of CD. Maintain a constant head in the tank. Note down the head H in the tank. Note down the length and breadth of the measuring tank. At time t is equal to 0, note down the level of water in the tank, measuring tank I am talking about. For a known time interval of t, say 30 seconds, 45 seconds, 60 seconds, note down the final water level in the tank. Volume of water collected in the tank is equal to area of the measuring tank into the depth. L and B of the measuring tank remains same, and the only variable is depth, H2 minus H1. Okay. Then actual discharge is given by volume divided by time. So, you know the volume divided by time will gives you discharge, that is your actual discharge. Then you have this CD is equal to actual discharge by theoretical discharge. Just now you determined the actual discharge. Actual discharge is equal to CD into theoretical discharge. Now theoretical discharge is equal to, by continuity equation, A into V. Now V theoretical is given by root of 2GH, capital H there, and A is the cross sectional area of the orifice or the cross sectional area of the jet at vena contracta. Most of the time we were supposed to take the area of the orifice, area of the jet at vena contracta, but most of the time we take this area of the orifice in order to calculate the value of theoretical discharge. Now what is the unknown? In this equation you determine the value of actual discharge, you determine the actual value of theoretical discharge, calculate the value of CD. Now once you find the value of CD, you already determined the value of CV, therefore CC is equal to CD divided by CV. Okay. So any doubt? I hope you are clear in this. Let us start with a simple problem. It's a very simple problem. So the height of water over the center of the orifice of diameter 20 mm is 1 meter. The actual discharge through the orifice is 0.85 liters per second. Find the coefficient of discharge. Very simple one. Okay. What is given? Dia of the orifice, D is 20 mm, convert that into meters, 0.02 meters. Calculate the value of area. Area is equal to pi d square divided by 4. Therefore area works out to be 0.000314 meter square. Then what is the value of capital H? Capital H is 1 meter given. Actual discharge 0.85 liters per second. Remember in the last class I said, if you divide this liter divided by 1000, automatically it will be converted into meter cube per second. Convert this into meter cube per second. Therefore Q is equal to 0.00085 meter cube per second. Now theoretical discharge is given by Torricelli's equation. V theoretical is equal to root of 2GH. You know the value of capital H that is given in the problem. Therefore find the value of V theoretical. V theoretical is equal to root of 2 into 9.81 into 1, that works out to be 4.43 meter per second. Theoretical discharge is equal to Q theoretical is equal to V theoretical into area of the orifice. This is what I mentioned just now. Okay. Now this is equal to, so look at this, this is 4.43 into area of the orifice which you calculated just now. So if you put these two values, you are going to get the theoretical discharge. Theoretical discharge is equal to 0.00139 meter cube per second. Then what is the value of CD? CD is equal to coefficient of discharge. Coefficient of discharge is equal to actual discharge divided by theoretical discharge. Actual discharge is this much, theoretical discharge is this much. This divided by this will gives you the value of CD, and CD works out to be 0.61. A very simple problem. This is a very interesting problem. Okay. So most of the time when you look into the question papers, whether it is a competitive exam or a university question paper, you are going to see this type of problem. So what is the speciality of this problem? Now the speciality of this problem is, there is a tank, there are two orifices. Okay. Here if you look at this figure, there is an opening here, there is an opening here. Now this is a jet profile from orifice 1 and this is a jet profile from orifice 2. So this jet and this jet, they meet at a common point. Okay. The question asked is, what is the value of x comma y for this case? I repeat, there are two orifices. From the two orifices there are two jets emerging. These two jets are meeting at a common point. The idea are, in the problem you are asked to find what is the coordinates corresponding to this common point P of x comma y. Look at this. A tank has two identical orifices in one of its vertical sides. The upper orifice is 3 meter below the water surface and the lower one is 5 meter below the water surface. If the value of CV for each orifice is 0.96, find the point of intersection of the two jets. Now look at this. Now the first orifice is at a depth of 3 meter from the free surface. The second one is at a depth of 5 meter from the orifice. In other words, this total depth is 5 meter and this depth is 3 meter. Therefore, from orifice 1 to orifice 2, the vertical distance is 2 meters, 5 minus 3. Now, let us start with the data given in the problem. Height of water from the orifice. I am talking about first one, I am talking about orifice 1. Corresponding to this orifice 1, the value of this depth of water is 3 meter. Now from orifice 2, my capital H2 is equal to 5 meter. Now CV for both the orifices is 0.96 given in the problem. Okay, this is the data given in the problem. So I said our aim is to find this P coordinates x comma y. That's what I mentioned here. Let P is the point of intersection of the two jets coming from orifice 1 and 2. Let P is the point of intersection of the two jets coming from orifice 1 and 2 such that now this is my horizontal distance and from this point to, so y1 is the vertical distance from P to orifice 1. So look at this, from this point to this point I call this as y1, and from the second orifice, the center of the second orifice to the point P where the two jets are meeting, that we call it as y2. Vertical distance of P from the orifice 1, that is y1, vertical distance of P from orifice 2, that is y2. Now what is y1? y1 is equal to, so y2 plus, this is 5 minus 3, that is y2 plus 2. Okay, what is y2? y2 is, look at this, okay, from this point to this point, that is y2. Now what is y1? y1 is this distance, so this distance is equal to, so y2 plus 2. Okay, in other words, this is unknown plus, I said at the beginning, this total depth is 5 meters. Out of that you subtract this 3, that is from the distance from first orifice to the second orifice is 2 meters plus from orifice 2 to this point of this point P, it is y1. Therefore this y1 y2, this y1 is equal to y2 plus 2 meters. Now define this coefficient of velocity for orifice 1, coefficient of velocity for orifice 2. So we already derived an equation this for this coefficient of velocity. Coefficient of velocity is given by x square divided by 4yh under root. Okay, x square divided by 4yh under root. Now in this case, if you look at this, okay, so kindly put this x square here, x square here. Okay, x square is missing here, so kindly put x square and x square. Now so CV for orifice 1 is equal to CV for orifice 2. In other words, the coefficient of discharge for orifice 1 is equal to coefficient of discharge for orifice 2. That is, this is the given condition. CV1 is equal to CV2. Now x square divided by 4y1 h1 is equal to x square divided by 4y2 h. If you simplify this, you are going to get a relation between y1 and y2. I repeat, in the given problem there is a definite relation between CV1 and CV2. So in this case CV1 is equal to CV2 is equal to 0.98 given. I know the equation for CV1, I know the equation for CV2. CV1 is given by x divided by 4y1h under root x square, sorry, and CV2 is equal to x square divided by 4y2h. Equate these two equations and you are going to get a relation for this y1 and y2. What is this relation? 3y1 is equal to 5y2. Now if you go back to the earlier step, look at this. I have one more relation. What is this relation? My y1 is equal to y2 plus 2. y1 is equal to y2 plus 2. This is one relation. Then this y1, 3y1 is equal to 5y2, or y1 is equal to 5 divided by 3y2. If you substitute the value of y1 in the earlier relation, you are going to get the value of y2. Now if you substitute that and if you simplify that, the value of y2 works out to be 6 divided by 2, that is equal to 3. Now y2 is 3. Now look at this, 3y1 is equal to 5y2. Now y2 is 3, therefore this becomes 5 into 3 is 15. 3y1 is equal to 15 and y1 is equal to 15 by 3, that is equal to 5. That is the value. Okay. Now knowing the value of y1 or y2 and given the value of CV1, the value of x can be easily determined. That is what I did in the next step. Now CV2 is equal to x square divided by 4yh. Therefore substitute the values. This is given in the problem 0.96. You find the value of x is equal to 7.436 meter. Since x square is missing, I think probably there is some change as far as this answer is concerned. Again I repeat, now kindly go back to the derivation what we derived. Now look at this, CV is equal to x square divided by 4y whole thing under root. Yeah, I think then the equation what I gave is perfectly alright. Okay, absolutely don't change anything. So only thing is you need to remember here in case of this derivation I did a mistake. Rather than putting a capital H, I put a small h. Now in this case I put this entire x square divided by 4yh under root, whereas in the problem root of x square is x, therefore x divided by root of 4yh. That is another form. You can stick on to this or you can stick on to that. But the procedure what I explained is perfectly alright, and whatever the value I presented there is perfectly alright. No change. Only thing is my sincere request to you is here kindly change the small h to capital H. Hope it's clear. Okay, don't change anything. If you want to put everything under root, then it will becomes x square divided by 4yh whole thing under root. So you're taking this x out of the root, therefore this becomes x divided by 4yh under root. Now this answer is perfectly alright. So the value of x is 7.436 meter. That is at a distance of 7.45, these two jets are meeting at a common point. I hope it's clear. Then the next and the most important one when I am talking about the orifice is time of emptying a tank through an orifice at its bottom. Suppose there is a tank is filled with water. If I provide an opening or a hole at the bottom, okay, how much time it requires in order to empty this tank? That the question asked. Okay, so what is the equation? Okay, if there is an orifice provided at the bottom of the tank, okay, knowing the value of the depth of water in the tank, okay, I need to know how much time it takes for the orifice to empty this water in the tank. So look at this. This is the tank. At the bottom of the tank there is an orifice, and here, so I represent this as capital H, H1 and H2. What is this capital H1 and what is this capital H2? Now before opening this orifice, I repeat, before opening this orifice, this is the depth of water. Now if you open this orifice for a time interval of say t seconds or t minutes, at the end of t, okay, this is the depth of water present in the tank. When time t is equal to 0, the depth of water in the tank is represented as capital H1. Now at time t is equal to t, once I open the orifice, the depth of water in the tank, I represent this as capital H. Then I also represented another two things. One is small dh, the other one is this h. What is this h? H is the depth at any instant of time. The moment once you open the orifice, at any instant of time, okay, the depth in the tank, I represent this as small h. Okay. Then what is dh? dh is a small strip at time t is equal to t, at any instant of t. So dh represents the thickness of the fluid film or liquid film. Okay. With that, let us see how to derive this equation. Let us consider a liquid tank of uniform cross sectional area A filled up to a height of capital H1. Remember, from here afterwards, most of the time, rather than talking about fluid or liquid, let us talk about water, because we civil engineers most of the time, so we encounter with water rather than other fluids. Very rarely we are talking about oils, but most of the time civil engineers deal with water. So there is a tank, and this tank contains water up to a depth of H1. Consider an orifice of cross sectional area small a fitted at the bottom of the tank. The one what you are seeing here is an orifice having a cross sectional area small a. Let in the period of time t, the liquid level in the tank falls from a capital H1 to H2. I said here my small t is equal to 0. Okay, the moment you are opening the orifice, and when my small t is equal to capital T, the depth of water in the tank, I represent this as H2. Consider an elemental strip of thickness dh at a height of h from the bottom. That is what I mentioned here. The moment once you open this, at any instant of time, okay, the depth of water in the tank, I represented this as small h, and at that depth consider a small strip of thickness dh. Now that is, at this instant, if you take delta t, that is in a very short interval of time, the depth falls to this dh. Therefore, volume of liquid discharged from the tank in time, this delta t is, I represented this as dq. dq is equal to area of the tank into minus dh. I repeat, so dq, the discharge in this short interval of time is given by, so the volume of this strip, the volume of this strip is given by the area of the tank into this depth, that is dh. That is what I represented here. dq is equal to minus a into dh. What is this minus sign? Because here this is the initial level. The moment once you open this, so the level of water or the depth of water just starts falling. That is the reason I put a minus sign here. Clear? Now the negative sign is used because h is decreasing with the increase in q. This is what I mentioned just now. Now we know the equation for this theoretical velocity. Theoretical velocity through the orifice is given by v is equal to root of 2gh. Discharge through the small time dt is equal to, so coefficient of discharge into the area of the orifice into the theoretical velocity. So here it is divided by, so divided by time. Now if you substitute these values, this dq is equal to cd into a into root of h into dt. Okay. Now this is for this small interval dh. Now you have the limits. What are the limits? Capital H1 and H2. So that is what I mentioned here. Volume of liquid discharging through the orifice will be equal to decreased volume of liquid in the tank. Okay. Therefore, it is minus a into dh is equal to cd into a into root of 2gh into dt. What you are looking for? What is your aim? At the beginning I said your aim is to find the time taken by this orifice to empty the tank. Therefore, dt is equal to minus A into dH divided by CdA into root of 2gH. Okay. So, now if you integrate this equation between the limits, upper limit and lower limit, okay, you are going to get the value of this t. That is what we are going to do in the next slide. Look at this, dt is equal to, okay, the same equation. Now, the total time t for emptying the tank can be calculated by integrating the equation from h1 to h2. Therefore, this 0 to t dt is equal to, the lower limit is h1, the upper limit is h2 of this formula. If you simplify this equation, you are going to get this t is equal to the time required by the orifice to empty the tank is equal to 2 into A. What is A? A is the area of the tank into root of h1 minus root of h2 divided by CD into area of the orifice into root of 2g. I repeat once again, the time taken by the orifice to empty the tank is given by 2 into the area of the tank into root of h1. What is h1? Before opening the orifice, what is the level of water in the tank? That is your h1. Now, at time t is equal to capital T, the depth of water in the tank, we represent this as h2. So, root of h1 minus root of h2 divided by the coefficient of discharge of the orifice into the area of the orifice into root of 2g. Okay. Now, in this case, remember, kindly we will go back to the figure. If you look at this, my depth falls from h1 to h2. Suppose if I allow this water to further fall or totally empty this, what is the value of h2? My h2 is equal to 0. I repeat, in this case, my depth varies from capital H1 to H2. That is, in this case, I did not allow the water to empty completely from this tank. Now, suppose if I want that condition, so the initial level is h1, if I want to empty this complete tank, then what is the time taken by this orifice to empty the tank? In that case, the value of h2, that is, this is the time when the tank becomes empty, corresponding to that my h2 is equal to 0. That is what I put it in the next step. Look at this, h2 is equal to 0 when tank is empty. If you put h2 is equal to 0 here, this equation reduces to t is equal to 2a into root of h1 divided by cd into a into root of 2g. This is how you are going to calculate the time taken by the orifice to empty a tank. So, knowing the area of the tank, the area of the orifice, the coefficient of discharge of the orifice, and also the value of h1. What is the value of h1? h1 is, before opening the orifice, what is the depth of water in the tank? If you know these 3 or 4 variables, capital A, small a, CD and h1, you can easily determine the time taken by the orifice to empty the tank. Okay? This is about, so time of emptying a tank through a orifice. Let us see a simple problem on this. A circular tank of diameter 4 meter contains water up to a height of 5 meter. The tank is provided with an orifice diameter 0.5 meter at the bottom. Find the time taken by water to fall from 5 to 2 meter. My value of h1 is 5, value of h2 is 2 meters in this case. For completely emptying the tank, second case, that is h2 is equal to 0. Take coefficient of CD is equal to 0.6, a straightforward problem. Now, let us straight away go to this equation. T is equal to 2a into root of h1 minus root of h2 divided by CD into a into root of 2g. Now, find the a, capital A. Now, diameter is 4, therefore, area of the tank is 12.56 or 57 meter square. Dia of the orifice is 0.5, therefore, area works out to be 0.1963 meter square. So, initial depth of water is 5 meter, final level is h2 is 2 meter in the first case. In the second case, my H2 is equal to 0. In this case, just now we calculated the value of capital A, the value of small a, CD is given in the problem as 0.6 and this is 5 and this is 2, substitute the value and find the value of T. Now T works out to be 39.58 seconds in the first case. In the second case, H2 is equal to 0. In that case, the formula reduces to T is equal to 2A into root of H1 divided by CD into A into root of 2G. Now H1 is 5 meters and small a you already calculated, substitute these values and you are going to find this H2 is equal to 107.7 seconds. This is a type of problem you are going to encounter in case of time of emptying a tank using an orifice. So I wrap up this session at this stage. So we will continue with some more problems and mouthpieces in the next class. Thank you.